All right, today we're diving into the invisible architecture of our world, organic chemistry. It's the science that connects the fuel in our cars, the clothes on our backs, and even the DNA that makes us who we are. So let's get into it. So let me start with a question for you. What could you, your own DNA, and the gasoline in a car possibly have in common? I mean, they seem like they're from completely different universes, right? But deep down, at the molecular level, they all share a fundamental secret. And that secret is organic chemistry. It's the incredible science of carbon. Everything we just mentioned, plus millions of other things, from life-saving drugs to plastics, is all built around this one single element. So what's the big deal with carbon? Out of all the elements on the periodic table, why is it the chosen one for building the incredibly complex molecules that life depends on? Well, let's take a look at its unique skill set. Honestly, you can think of carbon as the master architect of the molecular world. It's like the ultimate Lego brick. It has this unique power to build these huge, stable frameworks for pretty much everything, from simple gases to the unbelievably intricate double helix of our DNA. Carbon's power really comes down to two main superpowers. First up is tetravalence. Every single carbon atom can form 4 super strong bonds with other atoms. And second is catenation. Its amazing ability to link up with other carbon atoms, forming these long, stable chains and complex rings. Seriously, no other element can build structures quite like this. You know, for a long time, scientists actually thought these carbon compounds were, well, magical. They believed they could only be made by living things, thanks to some mysterious vital force. But that all came crashing down in 1828. A chemist named Friedrich Wöhler was just trying to make a simple inorganic salt, and he accidentally made urea, a totally organic compound. This one experiment proved that the chemistry of life wasn't magic. It followed rules that we could understand and even replicate in a lab. Okay, so if carbon can build millions upon millions of different structures, how on earth do chemists keep track of them all? They needed a really clear and consistent way to draw their molecular blueprints. And this is a huge challenge, right? You can't just write a carbon thingy on a piece of paper and expect anyone to know what you mean. Chemists needed a precise, visual language to map out exactly how every single atom is connected to every other one. So to solve this, their system kind of evolved over time to become more efficient. They started with what's called the complete formula, where you draw every single atom and bond. Super detailed, but wow, it gets cluttered fast. That led to the condensed formula, which cleans things up by grouping atoms. But the real game changer was the bond line formula. It's this elegant shorthand where lines are bonds and the carbons are just implied at every corner and end. It's brilliant. Now, this shorthand isn't just about saving a few seconds. It's really about clarity. By getting rid of all the visual noise from the carbon and hydrogen atoms, chemists can instantly see the molecule's core skeleton and focus on the parts that are actually going to be doing the interesting chemistry. But here's the thing, molecules aren't flat drawings on a page. They exist in 3D space. So to show this on a 2D surface, chemists came up with a really clever trick called the wedge and dash system. Just like you see here, a solid wedge means that bond is popping out of the screen, coming right at you. A dash line means it's going back, away from you. This simple little code lets chemists see the true 3D shape of a molecule just from a flat drawing. Okay, so we can draw them, but what do we call them? With millions of different compounds out there just pointing and saying, that one isn't going to cut it. We need a universal naming system. And this is so important because science is a global conversation. A chemist in Brazil needs to know exactly what a chemist in Japan is talking about, with zero ambiguity. They needed a name that could only describe one specific structure. So in the old days, we had common names. Formic acid, for example, got its name because it was first found in ants, and the Latin word for ant is formica. Kind of cool, but not very systematic. That's why the International Union of Pure and Applied Chemistry, or IUPAC for short, created a universal system. An IUPAC name is basically a GPS coordinate for a molecule. It gives you a precise, rule-based address that any chemist anywhere in the world can decode. So how does this chemical GPS actually work? It's a surprisingly logical 3-step process. First, you find the parent, which is just the longest continuous chain of carbons you can find. Step 2, you number that chain, giving every carbon an address. And step 3, you just name any branches that are sticking off that main chain, using their numbers to show exactly where they are. It's a really elegant system for organizing all that complexity. So let's recap. We have millions of molecules. We can draw them and we can name them. But how do we organize them all?
We can't just have a giant unsorted phone book of molecules. Chemists needed a way to sort them into families based on how they behave. And the solution to this filing problem is something called the functional group. Instead of getting lost in the entire carbon skeleton of a molecule, chemists learned to focus on specific, reactive little clusters of atoms attached to it.
So what exactly is a functional group? Well, you can think of it as the molecule's center of reactivity. If the long carbon chain is the molecule's backbone, the functional group is its active part. It's the bit that actually does the work and determines how the molecule is going to react with other things.
Let's look at a few quick examples. Any molecule, no matter how big, that has an OH group on it belongs to the alcohol family. If it has a COOH group, it's a carboxylic acid, like the acetic acid in vinegar. And if it has an NH2 group, it's an amine. You see the pattern? Just one small group of atoms defines the chemical personality of an entire family.
And this quote just nails it. The carbon chain might give a molecule its size and shape, but the functional group gives it its personality. It's what determines if a molecule is acidic or basic or reactive or stable. So the key takeaway is this. If you can identify the functional group, you can predict how a molecule is going to act. So we've seen the ultimate building block, carbon. We've seen the blueprints chemists use to draw it, the GPS they use to name it, and the families they use to organize it. That's the whole toolkit. And it raises one last really exciting question.